Good day! Welcome to the Atom Part 3. We're going to be talking about the symbols that we use to talk about atoms. Now, symbols for talking about atoms have existed since before we knew what atoms were. If you look 1670, Basil has got a whole group of symbols for different chemicals. The alchemists were doing a couple of different things. One, this is before patent law, so in order to protect their trade secrets, they would encrypt. Second of all, this made life a lot easier. They listed out their chemicals and then created a bunch of symbols that made sense. Now, there's a whole lot of symbols there for a lot of different things. It's a mess. So we started sorting things out. Once we started figuring out elements, we then moved on to John Dalton. This, once again, the guy that really comes up with the idea of the atom. Dalton creates a series of symbols for his atoms. He's thinking of atoms as what we call billiard balls, so hard spheres, and so his symbols represent that. Now, Dalton's symbols were pretty good, except for the fact that things got really complicated really fast. When you had a half dozen elements, not bad. When you got 118, well, there's a different story. So let's talk a little bit about modern symbols. To make things a lot simpler, instead of trying to draw circles with weird lines and dots and wavy things in them, we simply decided that the symbols were going to be a one-letter abbreviation for the element. However, you got more elements than you have letters, so that's not going to work entirely. So we have one-letter abbreviations and we have two-letter abbreviations as well. When you got a one or a two-letter abbreviation, the first letter is always a capital. If it's a two, or in the rare case of a three-letter abbreviations, the following letter or letters will be lowercase. So up in the upper right-hand corner, we have the symbol for lithium. Notice the capital L and the lowercase I. It's a two-letter symbol. When we talk about chemicals, when we write the symbols to describe the elements in the chemical, we won't have spaces, we won't have punctuation. So two uppercase letters together will tell us it is two different elements. Uppercase, lowercase will tell us it is the two symbol of form of a single element. Now, not all symbols are simply the abbreviation, because once again, things can get a little bit interesting. Now, we've got things like carbon. Carbon is C. That's pretty straightforward. Cobalt, CO. Okay, that also makes a lot of sense. Chromium, okay, we did a CR instead of a CH. You know, we can kind of see what's going on. That the H doesn't really have a lot of pronunciation in chromium, so that still makes sense. But what about AG for silver? Well, what's taking place is that some of the two-letter abbreviations are coming not from the English name, but from the Latin name. So let's see if I can butcher this. Argentium? I always butcher silver. Anyways, notice the Latin word. The Argentum, however you pronounce that. First and third letter, Ag, so that's silver. Copper, coperium. Yeah, you can pronounce coperium. That's Cu. So Cu, there's no U in copper, but there is in coperium. Sodium, that's going to be natrium. Oddly enough, when we alphabetize chemicals, which is somewhat frowned upon because you can accidentally put two chemicals that should not be near each other pretty close, but when we alphabetize chemicals as chemists, we very often list sodium under N for natrium. If you remember the ancient Egyptians and they embalmed their mummies using natrium, that's where the name comes from. Natrium, the mineral, is basically a mix of table salt and baking soda, both of which contain sodium. And of course, we got sulfur, which is just, S. Now, we've loaded these guys with a bit of information, stuff we've already talked about. So if you got the symbol in the middle, you've got your atomic symbol, or sometimes referred to as your nuclear symbol. We'll talk more about that in Unit 12. Generally, you don't have all of this information on all of your symbols. You leave the stuff you don't really care that much about out. In the middle is the elemental symbol. So this is O. O is for oxygen. We now have four corners. The bottom right-hand corner, the one that does not have a number in it right now, will get a number in Unit 4. That's going to be the number of atoms of that element inside of your molecule or formula or whatever. We'll deal with that in Unit 4. Lower left, however, that's your atomic number, number of protons. Upper left, that is your atomic mass number, number of protons plus number of neutrons. This number can change, and you would have two different isotopes, so remember that from earlier. Upper right, that is your charge. That is going to be protons minus electrons. Now, quite often we also like to think about these things not necessarily about atomic mass or charge, but about valence electrons. Remember, the valence shell, that's the outermost electrons that are packed around the atom, are the ones that interact with the world and the ones that govern the chemical reactivity for the most part. The Lewis symbol is a different way of writing them, in a way that shows the number of valence electrons. 1 dot is 1 electron, 2 dots, 2 electrons, you get the pattern. Electrons tend to like to pair up, so 2 dots together show what we call a lone pair, or just a pair of electrons that are hanging out in the same orbital. The electrons spin, you can get 2 in one orbital if you do one way and one spins the other way. We can sort these out by looking at the periodic table, and we'll actually talk a little bit more about this here a tad later on, but figuring out how many valence electrons you've got. So you can look at, say, the element oxygen. You know it's got 6 valence electrons. Once again, we'll talk a little bit more about that here in a little bit. Then you take the symbol, you draw an imaginary box. Obviously, I can't draw an imaginary box, so I've got a box. And you start putting electrons one by one on the 4 sides of the box. The sides of the box, in many respects, represent the orbitals of the valence shell. The valence shell tends to be dominated by s and p orbitals, so you've got a total of 4 orbitals that tend to dominate your valence shell, and thus the 4 sides of the box represent those 4 sets of orbitals. I put them in one at a time. Electrons are kind of like people. If you don't have to have a roommate, why have a roommate? And then I continue filling in the dots as they go. Eventually, I remove the box. And that is my Lewis symbol. That will come back in Unit 5 because we can look at Lewis symbols and figure out the shape and the structure of molecules based on the Lewis symbols of the individual atoms. But we'll do that in Unit 5. Okay, how do I figure out the valence electrons? Periodic table is fairly convenient unless you're in the middle. In the transition metals, that pink box towards the middle, this guy. And then, of course, down here in the rare earths. Those are a little bit more difficult, but when you're looking at the other ones, you've got the farthest most edge, the alkaline metals, those have 1 electron. Then 2 electrons for the alkaline earths, then 3, 4, 5, 6, 7 for the halogens, and then 8 for the noble gases. Location, which column it is in the periodic table, is going to tell you how many valence electrons your particular atom is going to have. If you're in the transition metals, you generally don't write Lewis structures for those guys anyways, which is good because it's a little trickier. Okay, that's looking at symbols. Those Lewis symbols are going to come back with a vengeance in Unit 5, so you definitely want to be thinking about those for Unit 5. Otherwise, we're going to see more symbols as we go. So see you on the final part, part 4, here in a little bit.